In this lesson, we will discuss tools that will help you to debug and troubleshoot a VI. In this section, we will learn how to fix a broken VI. If the Run button appears broken, it means that the VI contains errors that prevent your VI from running. You must fix these errors before you are able to run the VI. When the Run button is not broken, it means you can run the VI. Some common causes for broken VIs include a broken wire because of a mismatch of data types, or a control wired to another control, or an indicator wired to another indicator, or a required input of a node is unwired. To find out why a VI is broken, you can view a list of errors by clicking the Broken Run button. The Error and Warnings tab lists all the errors in your VI. Let's look at this example of a broken VI. First, I'll click the Broken Run button to view the list of errors. We can see that the first error states that this wire connects more than one source terminal. Let's double-click the error to find its location on the diagram. There it is. I can see that I have connected the output of the add node to a control terminal, which won't work because they both output data to the diagram. I can fix this error by changing this control into an indicator, and it disappears from the error list. The next error in the list is that the divide node contains an unwired input that is required. Let's find the error by double-clicking it. If I wired this numeric constant to the required input of the divide node, I fix the error and it disappears from the error list. The last error states that two terminals of different data types have been connected together, which won't work. This is an error due to mismatched data types because we have a Boolean output wired to a string input. As I examine this error, I realize that the in-range string indicator should probably be a Boolean indicator instead, since this indicator will only have two states, either in range or not in range. Notice that when I replace the string indicator with a Boolean indicator, I have fixed the mismatched data types error. Now that I've fixed all my errors, my Run button is no longer broken and I can run my VI. In this section, we will walk through tools that will help you debug your code once your VI is running. If a VI is not broken and can run, but it produces unexpected or incorrect data or behavior, then you should use debugging tools and techniques to identify and correct logic problems in the VI diagram. Use the Highlight Execution button to view an animation showing the movement of data on the diagram from one node to another at a slower rate. This can help you get a better idea of the order of execution in your VI. You can also see the data values being passed along each wire. You can use the single-stepping buttons to see how data moves through your diagram one node at a time. So each time you click the single-step button, only one node on the diagram will execute. Another debugging tool is a probe. Use a probe to check values on a wire as a VI runs. If you have a complicated diagram with a series of operations, and any one of which might return incorrect data, you can use multiple probes to read the data values passed along any wire to check if your code is working the way you expect. Breakpoints are a debugging tool that allow you to pause execution at specific locations you designate in your program. When the VI reaches a breakpoint during execution, the VI pauses and the Resume button appears. You can then choose to single-step through execution using the single-step buttons, or probe wires to check data values, or check the values of panel controls, or click the Resume button to resume running the VI. I'm able to run this VI, but the results of this VI do not look correct. So now I'm going to try to debug this VI. First, I'll use the Highlight Execution button to animate the flow of data through the diagram at a slower rate. Second, I can use the single-stepping buttons to execute a single node at a time. In the Debugging tab, I will click the Step Over button to start single-stepping through the VI. Since Highlight Execution is still turned on, execution highlighting still shows the flow of data from one node to another. I can click the Step Over button after each node to step through the entire diagram. When I step over the last node in the diagram, gray lines appear. I can then click the Step Over button one more time to finish running the VI. Third, I can add probes to specific wires by right-clicking a wire and selecting Set Probe. The Debugging tab now shows an item for each probe. Now I'll run the VI. Notice that the probe section has updated to show the latest probe values. You can also view the latest probe value by hovering your cursor over a probe on the diagram. Double-click any probe item in the Debugging tab to highlight the corresponding probe on the diagram. By examining these probes, I can determine that probe 1 shows the correct temperature in Celsius, and probe 4 shows an incorrect value for temperature in degrees Fahrenheit. This means the mistake in this VI must occur in the nodes between probe 1 and 4. On closer inspection, it looks like our constants are incorrect. Let's fix that. The fourth debugging tool I'll show is the breakpoint. I'll set a breakpoint on the Add node by right-clicking it and selecting Set Breakpoint. Notice that now there is a numbered red dot on the Add node, which corresponds to a breakpoint item in the Debugging tab. Now, when I run this VI, the VI pauses when it reaches the breakpoint. Now I can start using other debugging tools, such as highlight execution and single stepping. When finished, I can either disable the breakpoint or delete the breakpoint if I no longer need it. When you are debugging code, be aware that floating point operations can return symbolic values to indicate faulty computations or meaningless results. Symbolic values include NaN or not a number, positive infinity, and negative infinity. NaN occurs when invalid operations take place, such as taking the square root of a negative number. Infinity occurs when an operation, such as dividing a number by 0, takes place. In this section, we will learn how to capture data from your VI. You can capture data from any controller indicator on a VI by right-clicking it and selecting Capture Data. You can view any captured data on the Capture Data tab, and it is now part of your project. You can rename captured data items to give them a more meaningful name. Double-click the captured data item to view it. Now you can explore the data, analyze the data, or export the data. You can also bring the captured data back into any VI in your project. Just drag the captured data item onto a VI panel or diagram. Also, you can capture data from all controls and indicators at the same time on the VI panel. To do this, select Data, Capture Panel Data. I can now see the captured data on the Capture Data tab. Rename it, and expand this item to see all the control and indicator data. Now I can double-click any of the control or indicator items to view their data. Lastly, I can go to Data, Capture Settings to select which panel items to include when I use the Capture Panel Data tool. By default, all panel items are included. When you save the project, the captured data items are also saved into your project. They now appear on disk in the NI Project Data subfolder as TDMS files, which is a NI file format. You might want to capture data from your VI panel when you want to capture the results of an indicator, capture indicator results along with the corresponding configuration control values, capture interesting data, capture unexpected data for debugging and troubleshooting, or capture real-world data to bring back into a VI for future testing. In this section, we will discuss managing and displaying errors. In this example, the VI tries to access a DACMX thermocouple channel, start a task, read data, and clear the task, but the specified DACMX channel does not support thermocouples. How can you handle and report this error? By default, LabVIEW automatically handles any error when a VI runs by suspending execution, highlighting the node where the error occurred, and displaying an error dialog box. The error dialog box will display to the user a numeric code and message that correspond to the error. This is called automatic error management. Let's see what happens when we run this piece of code, which will generate an error. When this DACMX create channel tries to create a task with a channel that does not support thermocouples, that node will result in a runtime error. Notice that automatic error management immediately suspends execution at any node that has a runtime error and launches an error dialog box. This dialog box gives you the option to either continue executing the VI or stopping the VI immediately. In most cases, instead of relying on automatic error management, you should use programmatic error management so that you can control how errors are passed and reported. To use programmatic error management for a node, wire its error output to the error input of the next node. If a node executes without an error occurring, the node will pass no errors on its error output wire. However, if a node executes and has a runtime error, the node passes that error on its error output wire. Most nodes will skip execution if they receive an error on their error input. However, shutdown nodes like DACMX clear task and close file will typically try to execute and shut down resources even if they receive an error on their error input. At the end of your VI, you can connect the error wire to a display error node, which reports error details in a dialog box if an error has occurred. Now, let's turn on highlight execution to see the behavior of programmatic error management. Notice that when the DACMX create channel node has a runtime error, it passes the error along on the error wire. The other nodes continue to pass the error along the error wire until the error gets to the display error node, which reports the error information to the user in a dialog box. By using programmatic error management, we were able to manually control how and when to report the error. If I now select the DACMX channel that does support thermocouples and run the VI, notice that there are no longer any errors, so the display error node does not display a dialog box. An error wire is an error cluster data type, which consists of status, code, and source items. Status is a Boolean value that reports true if an error occurs. Code is a 32-bit signed integer that identifies an error numerically. Source is a string that identifies where the error occurred. If the error cluster data type has a status of true and a code with a non-zero number, then it contains an error. If the error cluster data type has a status of false and a code with a non-zero number, then it contains a warning. By default, the display error node only displays errors. If you want this node to also display warnings, you must right-click the type of dialog input, select Create Constant, and set the constant to OK Message plus warnings. You've completed this module. Here is a summary of what you've learned.